Thanks. Hi again, everyone. A couple of comments. Number one, next week we're back to the Monday, Thursday schedule, so the Tuesday class was a one-time exception. Number two, I'm sharing the class notes that I write. I'm sharing them with Zeev and Snap. So maybe I'll give him a moment to say how those are available at the end of the class.
Or
Okay.
I can say
Yeah.
quickly that they're available on the Snap website. I'll put a link in the chat. But if you go to the summer school page, by the lecture schedule, you can see video and notes links.
Perfect. Thank you. Okay. Next item of business. I want to encourage you to keep asking questions. So actually, I want to fix one fairly big mistake that I made last class. This was about the Foster-Lyapunov drift condition. So last class, I said if there is some function, if there is some function v such that we have the following drift condition, and I don't know why this was in my brain, but for some reason it was. This is not the one. At least this is not the one from the Mine and Tweedy paper I referenced. The actual one, which is called CD2 in that paper, is GV of x is less than or equal to negative C f of x plus D as long as we're on some compact set, where f of x, not just for x, but the whole function, is bigger than or equal to 1. Oh, I'm sorry. Thank you for sharing. What? Oh, yeah, the screen is shared. Okay, the screen is shared. Um, okay, so the first condition is not the one from Mine and Tweedy. The second condition is. There was a question last class. Well, doesn't f have to be like uniformly bounded away from 0? And in fact, it does. Okay. So again, I'm going to assume that whatever the audience asks is probably true now. Okay. So with that in mind, we're going to move on to the topic of today's class. So a recap, we finished last class with the drift method. We were looking at the MM1 system and we were playing around with different test functions, polynomial ones, and we were recovering information about, say, the moments of the customer counts. Today, I want to start with something very similar, but it goes by a different name. It's called the transform method. Transform method. And the idea here is if we use a polynomial Lyapunov or test function, we can get something about the moments, but is there a test function that will give us information about the entire distribution? And the answer is yes. And that test function, let me just call it v of q, is going to be an exponential one. Okay, so that let phi be the Laplace transform, the expected value of v of q. And let's see what the Laplace transform gets us. Again, we're starting with a very simple system, the MM1, and so we're going to get everything about it. But that's just because it's simple. So to refresh people's memories, the generator with rate lambda, we have an arrival. So our Q gets incremented by 1 minus the old state. And then mu, indicator Q is bigger than 0, E negative alpha Q minus 1 minus E negative alpha Q. Okay, then we just factor things out. E negative alpha minus 1 plus mu indicator q is bigger than 0, e negative alpha q, e alpha minus 1. And we take expectations. Expected value g of v of q equals 0. How do we know it's equals 0? Well, the generator has bounded transition rates, and the Lyapunov function is bounded itself. So the condition, the lemma from last class is satisfied. We get lambda phi of alpha, that's this part, e negative alpha minus 1, plus mu phi of alpha, e alpha minus 1. No, I did not miss this indicator. I'm going to add it and subtract it. So minus mu probability q equals 0, e alpha minus 1. Okay, so I over here added and subtracted the indicator that q is equal to 0. And now we know that this equals 0, and you can see that we can basically rearrange things to isolate for the Laplace transform. We know that this probability is equal to 1 minus rho. So we can isolate for the Laplace transform. Phi, I'm going to skip the algebra. It's trivial in this case. 1 minus rho, 1 minus e to the negative alpha over e to the alpha minus 1 equals 1 minus rho, 1 minus rho e to the negative alpha. Okay, and this happens to be the moment generating function of a geometric random variable. Okay, so, right, now we see that if we use an exponential test function, we're basically working with the Laplace transform and the BAR, and we're able to recover the information about the entire distribution. Now, so far I was restricted to the MM1 model. We're going to leave that model in a second because I don't want you to leave today's class thinking, wow, I can do anything with this method. In fact, this stuff is um, I don't want to say fairly limited, but it does have its limitations. You can't get all of this information for free for just any system or any model. Okay, now a little bit about terminology. Maybe make a comment. So if you're somewhat aware of the literature on, let's say, steady state diffusion approximations, you've probably heard of the following thing. So this is terminology. And this is important to just get it correct in people's heads. We have the drift method. We have the transform method. We have something like the bar approach. And finally, Stein's method. Although method number 4 is already, Stein's method is already very different from the first three. So the drift method, I don't know that there is, or I don't know who is the person that is responsible for really introducing the drift method. Let me clarify that. People have been using the drift method or trying out different test functions since the 1950s and probably earlier. Um, I think the term drift method itself, this goes back to like Bruce Hayek and Srikant, more recently Srikant and Attila Arielmaz. So I don't know, like let's say 80s to 2012-ish. And really, the drift method is most of the time what it ends up being is using polynomial test functions. Okay, the transform method. Um, this is a term that I've heard for the first time coming from Georgia Tech, Siva Teja and collaborators. So the transform method is basically the drift method with exponential test functions. Okay. And you could say, well, shouldn't I just think of the transfer method as the drift method with exponential test functions? I would call that a fair assessment of things, but also, but it's different because exponential test functions tell you something about the distribution of the random variable, the whole distribution, versus moment information, let's say, with the polynomial test functions. Okay. So let's say, okay, transfer method is exponential test functions. What the heck is the bar approach? Bar approach is really continuous time systems with general model primitives. So um, general service times, general inter-arrival time distributions. And the key idea here is we have a specialized test function. It's exponential, e negative, say, alpha x, but there are some extra terms, and these extra terms are carefully engineered to make the BAR for the general primitive model to make it tractable. And this really is due to Masakio Miyazawa and Jim Dai. And I also have some work on that with them, but they were the big drivers of popularizing this approach. So basically, so that we understand each other, everything can be called the drift method. We call it the transform method or the bar approach when we specialize to certain settings. That's it. And Stein's method is not just about getting moment information, it's about getting error bounds on approximations. All right, let me pause, see if there are any questions. Okay. Now, so let's do another example just to show you how when the drift method fails to give something useful, and then how exactly does it fail. So the GG1 waiting time. Okay, so WN, so now this is the linear recursion. Okay, waiting time of nth customer to enter the system. Then the waiting time of the nth customer is equal to the waiting time of the previous customer uh, plus the service time of the previous customer minus the inter-arrival time of the current customer, and we write the plus, so it's the positive part, non-negative part. And for convenience, let's call this thing x sub n. Okay, so again, if you've never seen this before, I'm not going to go super deep into try to build intuition on this. I'm counting on people having seen this before. The waiting time, so the nth customer, how long will that person wait? Well, as long as the previous customer plus the service time of the previous customer minus the gap in time between the arrival of the previous and the current customers. And x plus, this is maximum of x and 0. Now assume that the system is stable. The expected inter-arrival time is bigger than the expected service time. Then Wn converges in distribution to W. This is the steady state distribution as n goes to infinity, where W equals in distribution to W plus X positive part. Okay, so how do we derive this expression? We basically replace Wn and Wn minus 1 with W. Okay, and crucially on the right-hand side, this W is independent of the X. Okay, so a lot is known about this expression, but let me just let me try and derive some useful properties from it using the drift method. So as a result, expected value f of W equals expected value f of W plus X positive part. Okay, for all sufficiently nice functions f. And this is what another instance of what I've been referring to as the BAR. Okay, quickly, why is it the BAR? We can think basically of this being one, if it's a discrete time Markov chain, it's like a one-step transition. And so this is saying that the distribution of W equals the distribution of the one-step transition, which is true under stationarity. Okay, so let f of W be W, because the linear test function did give us something useful. 1. Okay, expected value of W. So now I just want to use this BAR and see what it gives us. Expected value of W equals expected value of W plus X plus. And how do I deal with the right-hand side? Well, I just rewrite it as I add and subtract plus expected value of W plus X negative part. By the way, what does that mean? So X negative part, this is negative minimum X and 0. Okay, so this is a mouthful usually, but you think of it the following way. When X is negative, then this is telling us how negative it is, but the quantity is always actually positive. And some things that are true, maybe I'll zoom into here. If we have X is always equal to the positive part minus the negative part. So this is how I'm deriving that first expression, first equality. Okay. But now we related the expected value of W to this object. We've got another expected value of W coming out of here. So therefore, expected value or negative expected value of X equals expected value W plus X negative part. Okay. Now, what is this thing on the right-hand side? This is another way to write it is W plus X, indicator W plus X is less than or equal to 0. Okay, so this is the first relationship we derived using a linear test function. This quantity, expected value of X, this just depends on the inter-arrival and service time first moments. So this is known explicitly. This object I'm not sure what, it's some object relating to the waiting time, but it's not clear immediately that this is anything useful. Okay, but we'll remember it. Let's try again. Let's say, okay, we were not lucky with the linear test function. What about a quadratic test function? And this is the last one. We're going to move on from this stuff. Um, Expected value of w squared equals expected value w plus x squared. Okay, that is our BAR. Let me rewrite this right-hand side. This is just expected value, w plus x squared, indicator w plus x is bigger than or equal to 0. And again, adding and subtracting this indicator that w plus x is less than or equal to 0, I see that this equals to expected value, w plus x squared minus expected value, w plus x squared, indicator w plus x less than or equal to 0. Now I'm in business. So whatever this is, I'm going to leave it be for now. I'm going to focus on this object. You see, if I do the expansion, I get a w squared coming out, which is going to cancel the left-hand side. And so let me do the expansion. W squared plus 2 expected value of x, expected value of w, plus expected value of x squared minus this expectation. All right, and now this object cancels with the left-hand side. And just rearranging terms, I see that -2 expected value of x, expected value of w equals expected value of x squared minus this weird object. Okay, and a couple of things to note, maybe I should have emphasized this. The expected value of x is negative. So this is why we see on the left-hand side this negative. It just makes everything positive. That's item number one. Item number two, we can divide both sides by expected value of x. Expected value of w is x squared over -2 expected value of x plus 1 over expected value of x dot dot dot. Okay, so this is an expression. Um, the only problem is we don't know what this thing is. Okay, now there has been a lot of work, a lot of research in understanding this object. This is basically the boundary behavior of the single server queue, of the Lindley recursion. And to summarize very briefly, this thing corresponds to, number one, the descending ladder heights of the random walk. The random walk given by the Lindley recursion. So this is kind of, we have a lot of theory about this stuff. Tying it closer to the queuing element, this equals expected idle period squared over expected idle period. So what this means is this object is related to the idle period of the GG1 queue. And the only thing I want to say about this is that this is a difficult quantity. It's a difficult quantity to analyze. So coming back, what did we show? We showed that, yes, we can get an expression for the expected waiting time, but the problem is it's got this very troublesome term that's difficult to analyze, and we're not going to be able to get any nice, clean, closed form expression for it. Okay. Except in the case where the arrivals are Poisson arrivals, then this term becomes very simple. All right. So that's how the drift method fails. Um, you can actually try the transform method. You can use an exponential test function and you will get something out of this. So um, there's a contrast between the two. All right, but now I want to move on. I spent about 25 minutes on this, and that's good. And I want to finally move away from the drift method and start to talk about the Poisson equation. Okay. And the goal for the rest of today is to discuss the Poisson equation, both in the Markov chain setting and the diffusion setting. We're going to talk about its solutions. We're going to talk about what this is, and we're going to set everything up so that next week we can start right away with the first example on Stein's method. Okay. All right. So let me get right into it. Here's the setup. Let X be a continuous time Markov chain on some defined on some state space E, which belongs to the grid. So delta is a constant, and so is D. The immediate question is, does it really matter that we have a Markov chain on the grid? No, it doesn't. All of this extends to the countable state space setting. I just want to talk about it in this context because it makes the notation a little bit simpler, but everything extends. Okay. And we have a generator for this Markov process, G, F of delta K. So what is the role of the delta? Let me just mention it very quickly. Suppose we have the MM1 queue, the single server queue. So the customer count is going to be an integer value, right? But in setting like in the setting of a limit theorem, we always scale the state space by some constant, like for example, 1 minus rho in the case of the M1 queue. And this constant, the scaling goes to 0. So what ends up happening is we start with, let's say this is a case where delta equals 1. We have a spread out grid space. And then as delta goes to 0, we push all the grid points closer and closer together, and that's how we eventually get a continuous approximation. Okay, but that's perhaps evident to people. So the generator, I'm going to sum over all possible values L, beta L at delta K. This is going to be the transition rate. So I'm just going to write it down and then I'll parse it. K plus L minus F of delta K. And delta K is in E. All right, so the generator basically says, I'm going to look at all, L should be, L is like the displacement vector. Okay, I start from delta K and then from delta, go to K plus L. And this here object is the transition rate. So this is the rate if I'm in state delta K that I'm gonna make a transition in the direction L, right? Um, let X have the stationary distribution of this Markov chain, which is assumed to exist and be unique. Okay, we're going to jump right into it. Lemma, and this is the Poisson equation. Given some test function h, set this is an important object, delta k h of x of t where so this is probably familiar to people, but whenever I use such a subscript on the expectation, what I really mean is that this is conditional on the initial value of the Markov chain. Okay. So let me parse what this object is. So this is an integral over time. I've got over here the stationary distribution or the steady state expectation. We should think of h. H is going to be a test function. We're going to vary h to be anything. For example, Lipschitz 1. We can think of h as a reward. So if h is an instantaneous reward obtained from being in some state x, then this function, it's called sometimes the relative value function. It is the value relative to the steady state. It is the value of starting at some state delta k for all time going forward. That's one way to think about it. The Poisson equation actually comes to us from the world of physics. Okay. Uh, and this thing is called also the potential. So we can think of this like the potential energy of starting at some state delta k relative to the steady state. Okay. So anyway, this function is important. We'll get more practice with it. So if it's your first time seeing it, don't worry. Okay. Now I need two conditions. Assume that condition number one, integral 0 to infinity Okay. Condition number one says simply that the potential is well defined. Okay. That's all I want of it. Because if condition one isn't satisfied, then we can't really say anything. And then number two, let me not write down the most general technical condition, but let me just say every state, delta k in the state space has finitely many destination or potential destination states. So in other words, if I'm in some state, there are only finitely many states to which I can jump to. This is, if you want to extend this lemma beyond this setting, you'll see that it's not very difficult to do so. But I don't want to bog the audience down with the most technical condition. Okay, so under these two assumptions, then this potential solves the Poisson equation. G f sub h of delta k equals expected value of x minus h of delta k. Okay. And this is all for all delta k in the state space. Few comments. Comment number one. I hope you start to see a connection. Why did we spend so much time on the drift method? In the drift method, it was all about choosing a good test function such that on the right-hand side, I get something usable, or I get some information about some performance metric of interest. There's one little typo, I'm sorry here. H of x. H of x. In Stein's method, what we're basically saying is I'm going to do the drift method analysis, and I'm going to use this very special potential Lyapunov function. Okay. And the good thing, or the powerful thing about Stein's method is that we don't need to come up with a Lyapunov function for the right-hand side to have some meaning or to be of use to us. The difficult part about Stein's method is that even though we have a formal, I'll say, closed form expression for the potential, we actually don't have access to many of its properties, or it takes some effort to get access to the regularity properties of this thing. And that is where the difficulty is compared to the drift method. In the drift method, you say you guess a quadratic test function. That's number one. Number two, before I start to prove this, especially for the people that have never seen the Poisson equation, you may be wondering, like, what do I do with this? Why is this even useful? So let me right away tell you why this is useful. So suppose we have y of t and Ito diffusion with stationary distribution given by the vector y. Suppose y is a good approximation, or we suspect that y approximates x. Then how can we evaluate things? So we start with the right-hand side of Poisson's equation, h of x minus h of delta k equals this generator. We set delta k, we let this be, say, the stationary distribution of the diffusion and take expectations. Therefore, we get expected value h of x minus expected value h of y equals expected value generator of the Markov chain. And now we subtract the zero. We subtract the generator of the diffusion. Why can we do that? This is at least an informal discussion. Why can we do that? Because this is the BAR. Well, of course, we need to verify, right, that f is sufficiently regular for this to hold, but this is the BAR. And now what do we have? We see that if we want to compare the two distributions x and y, all we have to do is we have to compare the generators of the Markov chain and the Ito diffusion. Okay, and this is the Stein's method step. Okay, so this is the big insight, that usually it's very difficult to work with the left-hand side, but the right-hand side is much more accessible. Okay, now if you are thinking about, like, if you're questioning whether this is true or not, right, you might be apprehensive about it because right now the Poisson equation for the Markov chain is not defined on the continuum. So that's the big technical caveat. And we're going to solve it. We're going to fix it. But you're absolutely right to think, no, this is fishy because the Poisson equation is not defined in the continuum yet. Okay. But that's going to be the topic of the prelimit approach. Anyway, so at the very least, um, I gave you a believable roadmap in order to uh, solve this or attack the right-hand side using Stein's method. We should really prove Poisson's equation. Okay, one more thing, one last thing. You might ask about condition number one, and how do I verify it? It's extremely important. So in practice, um, it isn't usually the bottleneck to things, okay? Maybe you need to think about it a little bit, but it's not a huge bottleneck. Suppose that the state space of the Markov chain is finite, countable and finite, okay? Then in a finite state space setting, this is always satisfied. Why? So let me just, I don't want to write it out again. Let me bring it to the next page. So when is this true? And I think the most important guidance is suppose we can show that this thing is decaying like some exponent sub-exponentially, okay? Then this is true, all right? When would we have this kind of exponential decay? Well, if the state space is countable, finite, then we have a Markov chain on a finite state space, and we know that it converges to its stationary distribution exponentially fast. So that's kind of trivial. Great. What about uncountable state spaces? Sorry, not account, infinite but countable state spaces. So we have, this is mine and Tweedy again, but condition number three, if we can show, if we can find the Lyapunov function that satisfies this drift condition, then this is basically, it's called V exponential ergodicity. V exponential ergodicity of the Markov chain, and um, not going to go into the I'm not going to go into the super details. So what I want you to just remember, we can show this exponential ergodicity by finding a Lyapunov function. Okay. And if you want to go to the detail or look into the details of things, you can go to the Mind Tweedy paper. There is one other method of verifying this directly by coupling the transient chain started at state delta k, coupling it to the stationary distribution. And depending on how much time we have today, I'll show you that, or I'll leave it to some other day. Okay, but again, let us go into the proof finally of the Poisson equation. Okay, so remember the generator. This is the sum over all displacement vectors, beta L delta K, f of delta K plus L minus f of delta K. The potential function, 0 to infinity, delta K H minus the steady state. And we want to show This is succinct. I'm gonna basically show you two arguments, and it's useful to have both or to see both. Proof number one, let tau be the first jump time. So now if for any epsilon, let me split this potential into two parts. So, okay, so there was a question. I am just seeing this in the chat. So why is it necessary that the integral part is less than infinity in the Poisson equation? Why is assumption one necessary? This, so maybe it's not necessary, but why I always think it's necessary, right? Is because here you have an integral of some function from 0 to infinity. Now, condition number one is basically like absolute, like integrability. If condition number one is not satisfied, then you can always rearrange this integral in some clever way that you can achieve any arbitrary value. So this goes back to like the absolutely summable series conditions. Okay? Basically, if this isn't satisfied, then this object is nonsense. It's not well defined even. Okay, so splitting this, and just for the sake of,
Sorry, there's a follow-up, which is the potential function seems related to the bias function.
yes, the potential function is the bias function. So yeah, I usually mention this, but right, bias comes from the world of dynamic programming, and there's the bias in something else, but yes, if you're thinking about this from the dynamic programming perspective, the potential function is exactly the bias function. I used to call it the bias, but I think potential sounds cooler. That's personal opinion. Um, let's see. So we're going to work with this so many times. Set h tilde of x of t. This is just going to be h of x of t minus expected value of h of x. Because otherwise it's going to make the algebra excruciating. Okay, expected value starting at delta k, h tilde x of t dt. Okay, now it's much cleaner. And tau, little mistake. Since I've got a random variable in the integrand, I should move the expectation outside. And this is another, why can I move the expectation outside? It's for being tonally. Infinity h tilde x of t dt. All right. Intuition. So I'm going to divide both sides by epsilon. Divide this by epsilon. Divide this by epsilon. Intuitively, as epsilon goes to 0, I'm going to call this 1. I'm going to call this 2. And I'm going to call this 3. So 1 is the simplest to understand. This is basically an integral from 0 to epsilon. So tau is the first jump time of the Markov chain. This is like an order 1 quantity. When epsilon is small, tau minimum epsilon is basically epsilon. We can formalize this make it rigorous, but it's basically epsilon. So one will converge to simply expected value delta k h tilde of x of 0, which this is h tilde, this is h of x minus expected value h of x. Okay. Two, we're going to show right now, this equals expected value delta k f sub h of x of tau minimum epsilon divided by epsilon. And then 3 is what it is. Therefore, 2 minus 3, this is going to be expected value delta k f sub h of x of tau minimum epsilon minus f sub h of delta k over epsilon. Okay, now if I were to get rid of this stopping time, then this does converge to the generator of the generator applied to the potential. Okay, so 2 minus 3 converges to the generator, 1 converges to this quantity, and if you've been keeping track of the algebra, you're basically just showed that the generator applied to the potential function equals the negative part of what I've circled. All right. So that is the Poisson equation. But now the only real thing to show is number 2. So let's focus on that integrand, or on that integral. So if I went fast, and someone wants to clarify something, please let me know. Okay. So this is a fairly straightforward argument, and this involves really the strong Markov property and the tower property. So the first thing we want to do is we want to use the tower property, and we want to condition on, so we got integral tau minus tau minimum epsilon infinity h tilde x of t dt conditioned on the value of the Markov chain at time tau minimum epsilon. Okay, now of course my external conditioning is on the value of x0, right? This one. Okay, so this is the tower property. Now, why can I get rid of this term? Well, this is the strong Markov property, right? Because I know the value of x at this stopping time. Therefore, what happened prior to the stopping time doesn't matter. Okay. Now let me basically say, yeah, write it nicely. Delta k integral tau minimum epsilon. I have expected value h tilde x of t dt pardon me, x tilde, given x of tau minimum epsilon dt. And now I'm just going to do a time change, or a change of variables, not a time change. delta k. So instead of starting, right, I know the value of x at tau minimum epsilon. So I can just shift everything. H tilde x of t given x0 equals x. Okay. Now, what I've written so far, hopefully I want to convey the intuition, but really, um, this is not rigorous perhaps, right? Because what's going on? What is this x of t? This underlying variable is basically saying, suppose I start off x from state delta k. What is the value of that x at the time of the tau minimum epsilon? But this x is not the same as the x inside the integrand. So what is perhaps the better way to write it down is if I initialize an independent copy of the Markov chain, right? And the initial condition of the Markov chain corresponds to the value of x, the first Markov chain at this stopping time. Not the best way to describe it, I'm sure, but I'm hoping that the writing is clear to people. Okay. Now, what I want people to realize is that this thing equals the potential function. And what is the initial condition of the potential function? The initial condition of the potential function is x tau minimum epsilon. So that the whole object is expected value delta k f sub h of x tau minimum epsilon. And then we're done. Okay, let me come back here. So this was our proof approach. We've shown that rigorously that 2 is equal to what I claimed it was equal to. And then rearranging things and taking epsilon going to 0, you can argue that this term converges to the generator. The one little hiccup is that, again, the presence of this random time tau in the argument. You have to be a little bit more careful about it and basically evaluate the cases where tau is bigger than epsilon and tau is less than epsilon. So it's not a fully rigorous, complete proof that I've provided you. Nevertheless, I'm confident that if you were to sit down and try to attack the presence of this tau, you could figure out the rest of the details by yourself.
There's a question in the chat from Eva.
In step one, yes, it should be h of delta k. Yes, thank you. Okay. I said there are two avenues to the proof. I'm not going to give you the full details of the second one because I want to make sure we finish on time. But what I do want to show you is another way. Another way. Okay. So let R be the sum of all possible transition rates from state delta k. Then what we can really do is probability. Well, let me see this. The integral 0 to infinity L minimum epsilon to infinity, value delta k, h tilde x of t dt. This can be analyzed directly because number one, probability that the jump happens after time epsilon. Well, this is, right, how much time does the Markov chain spend at its initial state? This is just E negative exponentially distributed amount with rate R. And this probability is the tail of the exponential distribution. Now, given the jump time happens before, we know that the value of x at the jump time, sorry, the h is not, h shouldn't be there, has a known distribution. Okay. Given the jump happens before time epsilon, where do we jump to, or the location of our first jump? This has the simple distribution based on the transition rates. So in other words, we can compute this directly. And then rearranging things, you'll again recover the Poisson equation. You can treat this as a homework exercise if you wish to solidify your understanding. All right, so that's that. Let me call it QED, even though technically I gave you just an overview of the proof. Any questions? Where do we use condition number 2? That's a good question. You would use condition number 2 if, say, you're using this approach. If you're evaluating this expression directly, you would need condition number 2. Otherwise, like, pathological things can happen, or you can come up with an example where this thing is not really tractable. So that's where it comes up. Okay, what's left? So that's the Poisson equation for Markov chains. I've given you the use of it. Let me talk fairly quickly about the Poisson equation for Ito diffusions. And then depending on how much time we have, I'll talk about verifying this integrability condition. Okay, so just to remind ourselves, given a drift vector B, and sometimes this is called a dispersion matrix. Let y solve dy t dy of t plus sigma dw t, where w is standard Brownian motion. Okay, now I kind of said this in last class that under some assumptions on sigma and b, the diffusion solves or satisfies Ito's lemma. Is there a clean assumption or is there a clean set of diffusions or class of diffusions which are going to satisfy what we need? And the answer is yes. Assume that B and sigma are such that the SDE has a strong solution. This is the key term, strong solution. Basically, if the SD has a strong solution, then we're safe in terms of using Ito's lemma. So what does that strong solution mean? Definition 5.2.1 of the book by Karatsas and Shreve. I'm going to call this K and S. Okay, a sufficient condition for a strong solution is number one, B of x minus B of y, and sigma of x minus sigma of y is less than or equal to and B of x squared sigma of x squared less than or equal to k squared 1 plus x squared. So this is one sufficient condition. And basically you see that if the drift B and the dispersion matrix sigma are Lipschitz, then everything holds. So this is what I meant last class. It'll all boil down to basically assuming that the primitives are Lipschitz. So, okay, we assume that. Maybe a comment, right? In practice, you rarely try to prove something using Stein's method for like a huge class of models. In practice, you usually focus in, you already have your diffusion model in mind, meaning that if you're focusing in on one model for many months, you're probably going to verify all of these conditions for it as well. Okay, let Y denote the stationary distribution of the stochastic process, which we assume to exist and be unique, and we're going to assume that the diffusion is ergodic. For convenience, Aij, this is sigma I, sigma j transpose, where sigma I is the row or the ith row of the entire dispersion matrix. Define the generator. Gy is the limit, standard limit, 1 over t, expected value f of y of t minus f of x. So the generator satisfies gy sum 1 to d. If the dimension is tripping you out and giving you a hard time, just think that d equals 1. Consider the one-dimensional setting. Once you understand the one-dimensional setting, it's fairly straightforward to generalize. Okay. So even though the stochastic differential equation is usually defined in terms of the dispersion matrix sigma, in practice, people really work with the, like the square of it. So people really work with the AIJs. Here we have the drift. So the drift corresponds to the first order term. The dispersion or diffusion coefficient corresponds to the second order term. Okay, so we've set up our diffusion process. What about the Poisson equation? Given H RD to R with the H being integrable, let H tilde be H of X and this little f be the potential again. We assume implicitly that this thing is again well defined. Again, how do you verify this? This drift condition is what I want to say. So regarding drift conditions, and this is maybe a little bit more for the experts who are familiar with it, we have this is the typical exponential ergodicity condition, but also this condition, the first condition I've written down, sometimes may be hard to verify. So there is also exponential ergodicity. There's also sub-exponential. Sub-exponential ergodicity. And basically what it means is that the transient distribution converges to steady state slower than exponential. It could be polynomially fast. But if you want to show that this integral is finite, it's actually enough to show that the convergence is at most or at least polynomially fast, like you know, perhaps inversely proportional to t cubed or something. And the typical setup is we have some function psi of v. I forgot whether there should be an x or not. I'm not sure about. So the psi, I believe, is usually convex or concave, one of those. So as a special example, if you can show that gv of x is less than or equal to negative c square root of v of x plus t, then we can get some kind of polynomial convergence to the steady state result. Okay, so what am I doing? I'm not giving you a comprehensive discussion on all of these conditions. I'm just pointing you to the fact that sometimes exponential ergodicity will be difficult to verify, whereas sub-exponential ergodicity will be a lot easier, and this will give you this integrability condition. All right. Okay. Plane G applied to the potential equals expected value. Well, it solves the Poisson equation. So we're not going to have enough time to go into this. I'm going to give you an outline of the proof. Proof idea. And this is going to look very simple, very similar to the Markov chain case. F we can split this into two cases. Okay. This term, this is number 2 again. This equals, we take the first expectation outside. We use the tower rule, and you can show that this integral number 2 in the exact same way it's just using the strong Markov property, or the Markov property even in this case. You can show that integral number 2 is basically looking at the value of the potential at the time epsilon. Rearranging things, we have expected value f sub h of the potential at time epsilon minus f sub h of x equals 2 over epsilon, 1 over epsilon, 0 epsilon, expectation h tilde of y of t dt. Now let epsilon goes to 0. Left-hand side converges to the generator. Right-hand side converges to, I missed the negative h of x, and this is tilde. Right? That's basically what we did for the Markov chain case. But now look at this and then try to answer to yourself, what's the problem with this argument? What do we assume here implicitly? And that as a hint, it's all about the left-hand side. Well, how we need to basically assume, in order for this thing to make sense, we need to assume the limit is well defined. In order for, right, so let's look at the generator. What is the generator? The generator applied to the function is a second order differential operator on that function. In other words, it only makes sense if f is twice differentiable, or it's C2. Let's just call it C2. Okay, so if we knew a priori that f is C2, yes, this is a complete proof. But we don't know, right? That's again this regularity coming up. We don't know that the potential is C2 a priori. So the question is, if we don't know that f is C2, how do we prove it? And the answer here is it's actually highly non-trivial. So let me give you just some context for this. And then some context, I'll talk about the Poisson equation, or the potential for a fluid, and then we're going to be done for today. Okay. Problem. Need f to be, let's say, C2. For GYF to be defined. Okay. Solutions. One, in special cases, can show that f is in C2 directly. That is what, yeah, we show directly one way or another, but you basically show it directly. For example, there's a classical setting. where the diffusion under consideration is the OU process, dy of t is negative y of t dt plus square root of 2 dw of t. And let's say this is dimension 1. Then the steady state distribution is the normal 0, 1. And the expectation, the transient distribution is known. And this is expected value h x e negative t plus square root of 1 minus e negative 2t y. Okay. In other words, right, this is the term that appears in the potential. And if we want to differentiate the potential, we have to basically differentiate the transient distribution. And for us to do that, differentiate it with respect to the initial condition. For us to do that, we need to know what the transient distribution looks like with respect to the initial condition. Notably here, it washes away exponentially fast, the initial condition. But other than this example, actually, I don't know of any other system where we know the transient distribution so clearly like we do here. Okay, so this is a one-off case. And you shouldn't rely on knowing the transient distribution. Okay, let me point you for proof of the Poisson equation. See Itai Gurvich's paper, 2014, Annals of Applied Probability. So exponential, I forgot the title. But he's got, I unfortunately don't have time to go over the argument. I will post, I've got it written down, so I'll share it with the SNAPP team. Just a quick proof outline of how you actually prove it. It's very slick. It's very slick. It's a really cool argument, but we're not going to have time to do it here. Okay. The last caveat. So I think I would call Itai's paper to be the definitive source on the Poisson equation for, let's say, unconstrained diffusions over the entire Euclidean space. He tackles the Poisson equation specifically in the setting of like diffusion approximation. So in the setting that's interesting to us. What I don't yet know of is a similar treatment. Poisson equation needs a similar treatment rather, so showing that the potential satisfies it when we have unconstrained. Oh, sorry, not unconstrained, constrained diffusions. Constrained diffusions, for example, reflected Brownian motion on the orthant in 2 dimensions. So this is something that bounces off the walls here and there. What is the difference between having a constrained domain and unconstrained domain? Basically, Itai's treatment of this, Itai's proof of this claim goes as follows. He says, well, we needed F to be C2. So Itai will use PDE theory, elliptic PDE theory, to show that a solution to the Poisson equation is C2. Kind of a priori, we have not knowledge about that. if we wanted to do the same thing for these constrained diffusions, we need to say that there is a reflecting boundary condition, oblique derivative problem. Okay, there's a PDE second order with oblique derivative reflecting conditions, and we need to know the regularity of that thing a priori so that we can apply the rest of the machinery. Now, I'm not saying that nobody has ever dealt with Poisson equations for these processes. It's absolutely not true. And I'm sure that there are papers I'm not aware of. I'm saying that if you want to go ahead and apply Stein's method to settings where your limiting distribution is some kind of RBM distribution, you've got to be careful, very careful with the uh, regularity of the solution to Poisson's equation. Okay, and this will come up in like derivative bounds. So maybe I just went off into the deep end, but that's okay. I didn't stay there for long. Okay, so last one, homework problem, and then I'll stop. Suppose we have a dynamical system, and the dynamical system is defined as follows. We have some kind of vector field. And what is this x up top? This is the initial condition. And this all lives in RD. Consider the potential 0 to infinity h of zx of t dt. So what is it basically saying? We have a deterministic dynamical system like a fluid model. For example, fluid model or mean field model. It's defined by the vector field F. This is the initial condition. You consider the potential. H is some test function to be determined. You can think of h of x equals x, for example. And this is the potential. Now there's nothing random here anymore, so it's actually simpler. What does, or show that, let's say in d equals 1, um, h prime of x times f of x equals negative h of x. Okay. So this is the basis of applying Stein's method for mean field and fluid models. We will probably not reach that part in the course, but this is a useful exercise. If you can do this, then it means you've mastered the idea of this. So splitting the integral into two slots. Okay, good. So we are done the preliminaries. Next class, I'm going to start with the first example. What is it I really want you to remember? I want you to remember for next week the BAR for the Ito diffusion and the Markov chain. And I want you to really remember the Poisson equation and its solution to potential. Okay. I'm going to stop here. If there are any questions, I'm happy to take them. Okay, maybe no questions. That's okay too.
All right. Well, thank you, Anton. I'll leave the room open in case there are any lingering questions. Um, and otherwise, see you all on Monday.
Maybe just one quick question. So when you say F is a C2, you're basically saying like the collection of, thinking of the collection of H's for which we'll get an F that is C2.
Yes. Yes. It's not right. You're right, exactly. Our degree of freedom is not the F, it's the H. So we just need to choose the H. Indeed, what I did not write in this claim is what is the condition required on H. So there will typically we'll work with Lipschitz H. Okay, that's a good point.
And I guess that's the idea, right? Like the bigger set of edge you can choose, the better you can bound the distance between
That right.
the
The more H's you can get bounds on, the more powerful your statement. I just want to modify one thing I said. It's it's not just like Lipschitz H. Really, the regularity of F is tied to the regularity of H. So the more derivatives H has, the more derivatives F is going to have. Yeah.
All right, cool. Thanks, Anton.
Sure.